Recording. Okay. So we can start the today in-class practice. Today we will discuss for a few hours. So we will cover the whole 3-hour slots, and we will discuss about applied transformers. We will review a few concepts related to self and cross attention that you have already seen with Professor Cagliero. We will see some models that are able to perform discriminative tasks, such as encoders. We will see how an encoder works, like specifically transformer-based encoders, transformer-based decoders, and sequence-to-sequence models. So we will see a few architectures. We will see BERT, GPT, and BART. We'll see how the attention is used in all those 3 architectures. Then we'll do some exercises. And if you don't mind, yesterday we had the lab on information retrieval and recommendation systems. It was quite long, so I will review the lab together with you with the solutions. And if you have questions, we can see you can ask questions and we can answer a question together. Then in the second part, we will see some task-specific transformers. We'll see how we can use transformers to perform specific tasks, such as text classification or name identity recognition. And finally, we'll do a very brief discussion on the tools that we can use to pass from development to production those models. So if those models are used almost everywhere now, and having a brief overview of what are the tools that we can use to deploy those models, I think it's useful for you besides the course itself. So to start, let's start with the introduction to the transformers architecture. So the transformer architecture was introduced in 2017. It was originally proposed for machine translation tasks. It means that it was able to perform some tasks such as the input is a string in a language. The goal is to translate that string in another language. So if I have models such as the one I have here on the right, I have JSON étudiant that goes into the model. Then I have a structure, a transformer structure that is composed of encoder and decoder modules. We will see how they works. And finally, I have as output the sequence in English. So if I have JSON étudiant in French, I will have as output I'm a student in English. What are the basic building blocks of the transformer architectures? For sure, the most important one is self-attention mechanism, also cross-attention mechanisms that are used in encoder and decoder models. And finally, we'll discuss also the positional encodings. That is a fundamental part of those architectures. For reference, the original paper now has got more than 30,000 of citations. It's actually last year, so it's very. It has gone to a very it has started a revolution in the field of natural language processing. So the most important part of transformer-based models is the attention mechanism. And actually, the self-attention mechanism is the power of behind, the most important thing behind the encoder-based models. So how self-attention mechanism works? We have word embeddings, and we know how to get those word embeddings. We can also randomly initialize word embeddings for some words. So we have a word and its associated vector. The goal is the first thing we do is to decompose this vector in 3 different vectors. So we can project this vector in 3 different vectors. We call them query, key, and value vectors. So each word is then associated to 3 different vectors. So we have a set of vectors for each word. And we have these query, key, and value vectors because they will be used to compute this self-attention and the attention mechanism in general. So how it works. So the idea is that we have a structure like this. I will go into the details of the steps that we use to compute the self-attention for words. So let's imagine that we have a sequence of 3 words. So we have W1, W2, and W3. So we have 3 words, and they associated value, key, and query vectors. So we have 3 vectors associated to each word. The idea of the self-attention mechanism is that to fully understand the meaning of a given word, we need to understand the context. And in this case, the context is given by all the other words in the sequence. So the self-attention is called self-attention and not only attention, because it computes the attention scores, we'll see how, between each word and the word itself and all the other words in the sequence. So because we compute an attention score for the word itself, it's called self-attention. So the first step of the self-attention mechanism is to use the query vectors for a given word and use it like here. We have as input the query vector. You can see that we have Q1, Q1, Q1. So we are computing the self-attention mechanism for the first word, the word W1. And the idea is that we have the query vector that we compute the dot product between the query vector and the key vector of the word. So we have the Q1 that is always the same. We are computing the attention between W1 and itself. So we compute the dot product between Q1 and Key1. And we obtain a given number because it's a row by column multiplication. So we have only one number. We do the same for all the other words in the sequence. In this case, we have Q1 that is always the query. So we are asking, with this vector, we are asking how much attention we should pay to the other words or the word itself. And so we have this query vector that asks how much information I should take for the other word. And so this is always the same, Q1, Q1, Q1. And we multiplied it for the key value, the key vector, sorry, for each different word. So we have Q1 multiplied by K1, Q1 multiplied by K2, and Q1 multiplied by K3. And we have all these 3 numbers. Okay, so the step after this computation of those scores is to apply a simple softmax operation such that after the dot product, these values become probabilities. So it becomes a number between 0 and 1, and they all sum up to 1. Sum up to 1 because we want to know how much probable is that I should pay attention to the same word or another word while computing the vector representation for a given word. So all these steps are done for the first word, right? So this is the first iteration for the first word. So we apply the softmax. We compute these probability scores. These scores are usually called attention scores because they give us an idea of the attention that I should pay to the corresponding word. And yes, then I just multiplied this vector, this number for the by the value vector, because you remember we have query, key, and value vectors. We use the query and the key, and now after the softmax, I just multiply this vector, this number, sorry, the attention score. So I can call it attention score. The attention score by the value vector associated to a given word. So then to compute the final representation of the word itself, so for the word W1, I just sum up all the representations multiplied by the attention score. It means that I give to some other words the weights given by this attention score. It's like a weighted sum of all the value representations of the word multiplied by using the attention score as coefficient for the weighted sum. So at the end of the process, what I have is a vector representation for the word W1. So this is the word W1 represented by the word embeddings and all the query, key, and value vectors. And as output, I have a processed version of these vectors of this word, and I have a representation of this word. All the things I said here are applied for the first word, so the word W1. Of course, this is done, this is done for all the words in the sequence. Okay. For all the words in the sequence, so I have the same process apply for the word W2. So here there is an example of the full process for the word W2, where I have here, you can see that query is always Q2 because it's associated to the word W2. So the idea is that this query vector asks all the other words how much attention I should pay to them and to the word itself. In the case I'm computing the self-attention for the word itself, how much attention I should pay to their vector to fully understand the meaning of that word. Of course, I'm oversimplifying a little bit because it's not a matter of words, but we have also subwords. So we have tokens instead of words, but it's just to give you the idea of how self-attention is working. So that's something we need to point out. The same process is done for each word in the sequence. So we are doing the same operation. So all these set of operations are done for each word in the sequence. So for word W1, we do all this process. For word W2, we do all this process. This is why the attention mechanism usually has a quadratic complexity, because we need to compute all these operations. So for each word, we compute n operations, where n is the number of words in the sequence, because we are computing the dot product by multiplying the query vectors by the key vectors of each word in the sequence, so n, but multiplied by n because we are doing this for each word in the sequence. So the complexity of this mechanism is n squared. Is it clear for you? Is something confusing? Okay. Okay, that's how self-attention mechanism works, yeah? Okay, I repeat just for the online. The question is why we compute the attention mechanism for the word itself rather than only for the other sequence of the words. So the idea is that it actually happens that if you don't compute the attention scores between the word and the word itself, it will lose the meaning of the word itself during the process. Instead, you want to propagate after the intrinsic meaning of the word. So if I have pen and if I have, I don't know, pencil, they are two different words. They can be found in the same context, actually. But if I don't compute the self-attention score between the word itself, I lose the information that this is a pen or a pencil. Is it clear? Okay. So what actually happens usually is that we have very high attention scores for the word itself by itself. So this score, so for W2, this score will be the highest one among all the others, because I want to know that this is a pen. And then, of course, I need to understand all the context. Yes? Yes. No, yeah. Query, key, and values are not a copy of the word embeddings, but they are a projection of them. So in principle, I can have word embeddings vectors that are like, I don't know, 1,2424 dimension, and then I can have, I don't know, query key and values that are like 512. So I can distinguish between them. How they are obtained? They are obtained by given a vector. I use an MLP, multi-layer perceptron, like a very shallow neural network, a layer actually, a single layer of neural network that pass from the input dimension here is the word embedding dimension, and the output dimension is the dimension that I want for V1, K1, and Q1. But I have three of them, right? I have three projection layers. So they are like the projection layer for Q, projection layer for K, projection layer for V, and I obtain the vector representations for query, key, and value for that word embedding. Is it clear? No. Query, key, and value are different vectors, are not the same between them. Okay, is it clear? They have the same dimension to match the dot product operations and so on and so forth, but they are different vectors. Yeah. So each word comes with its word embedding vector that can be randomly initialized. The thing is that it's then projected into three different vectors, and then in the transformer we have as a representation for inside the transformer. Actually, we have as representation for this word those three vectors. We carry on all these three vectors because we need them while computing all the operations that are reported here. So here I put this on the middle, but actually this is not used. This is like, okay, I apply my projection and I have these three vector representations that are actually V1, K1, and Q1. Is it clear? Okay, you're welcome. Just a check online, I don't know, because it's a very, okay, no question online. Yes, because it's very, like it's not trivial as a mechanism, and it's actually the foundation of all the modern transformer models. So if you are aware of all the modern transformer models, even, I don't know, GPT that produces text on the web, and all the fancy stuff that are coming from transformer models, they are basically most of the innovation in those models come from this self-attention mechanism that was actually introduced not in this paper, but it was introduced in 2015, but was used in this way for the first time by this paper. Is it clear? Okay. So this is how self-attention mechanism works. In the transformer architecture, we actually stack multiple layers of encoders. So we have multiple encoded layers stacked one after the other. Actually, I have an image here, but just I want to show you, just forget about the second part. The encoder, each encoder layer is composed of multiple operations. One is the multi-head attention, the attention that I explained you today with the simplification, because it's just what a single head does, but we can actually have multiple of them together. Then we have some operations like the addition of the vectors, the normalization. We have a feed-forward network to actually remanage the vectors multiple times. But we have as the basic building block, the most important building block is this one, like the module that performs the attention operation. Yes, in encoder layers, what we have in encoder architectures, so transformer-based architectures that are based only on encoder layers, we have multiple encoder layers, such as in convolutional networks, we have multiple convolutional layers stacked one after the other. And what we have here is that actually we have in BERT-based operation, BERT-based models, for example, we have 6 or 12 layers of encoder operations that are performed one after the other. How and why they can be performed one after the other? Well, because after the execution of these all these operations, we actually have another vector that is the same of having the word embedding here. So we actually don't change the dimension. We don't change the operations we do. So we have a vector representation, sorry, that is very similar, at least in terms of dimensions and so on, of what we have on the input. So we have a vector for each word in the sequence. So we can stack multiple of these layers in our model, and we can create a transformer-based encoder by stacking multiple encoder layers. What I want to point out here just briefly is the fact that we don't actually have just the attention mechanism, but we have multi-head attention. It means that the same process I explained to you before here is applied to actually with multi-head. It means that we have a vector. We have as an hyperparameter the number of head for the model. Let's suppose we have 4 heads. The idea is that we actually divide the vector into four equal parts, and we apply the same operation but on this subset. So here apply self-attention and the layer and so on, then apply self-attention here, self-attention here, and self-attention here. So the idea is that it's what I proposed you in the previous slide is just a little bit of a simplification, because this is what happened in a single head, and what actually happens in the full network is that we just split the vector in a fixed number of parts, and then we compute the self-attention and all this operation in each head. Why we have multiple heads? Just because having multiple heads, we can actually pay attention to different aspects of a given word. It's a little bit tricky to understand. I cannot go into the whole details of this, but the idea is that if you apply self-attention on this part, and then on this part, and then on this part, and so on and so forth, you can actually think that each head pay attention to different things. Like if you think about images, perhaps one head can pay attention to colors, the other to the contours, the other to other aspects of the image. In the text is a little bit fuzzier, but it's actually one can pay attention to the topic related to the word, the other one to the emotion related to the word. Actually, it's not very clear as this as a distinction because it's learned during the training, but the idea is that this works better than having a single head, and this is what is done in whole transformers actually right now. So we apply multi-head attention. Yes, question? Mm-hmm. No, this is not a this is not a subset of the word, but this is I can try to draw something here. We have W1, W2, W3. We have a vector, and we split this vector. Then we have this vector, and we split this vector. We have this vector, we split this vector. And what happens is that we have self-attention 1. We can go like, this is the first head of the attention. We compute this between all these 3. And then self-attention 2 is computed between all these 3. So the second position here. Yes, different parts of the same word. Like we split the vector representation of the word, not the vector representation, not split the sequence, like not the input sentence, but the vector representations. This is actually why usually we have the vector representation dimensions is usually a power of 2, because then we have a power of 2 also for the number of heads. And if we have 512, for example, as a dimension for the vector representation, so for each word we have a vector of 512, we can then split divided by 8, and then the dimension for the single head is 512 divided by 8. Is it clear? Okay, it's just to give you an intuition that the fact that we are now applying not like still self-attention, like the concept is the same, but we are applying it like in parallel in multiple heads, and so we are applying this on a sub portion of the vector itself. Okay, in encoder models, yes, and in encoder layers, we actually have the self-attention mechanism. So we compute the attention between each word, between the word itself and each other word in the sequence. But in the decoder model, in the decoder layers, because actually the original transformer was an encoder-decoder model, in the decoder layers, we have what we call cross-attention. We actually have both self-attention and cross-attention. The idea is the same, like is the same idea that we discussed a few minutes ago about self-attention. But the idea is that instead of having the query, the keys, and the values coming all from the same source, so in that case was like the inputs, the words, word embeddings, and so on, they all come from the same input sources. We actually have the attention score is performed on queries generated from one embedding and key and values generated from another source. What we actually want to do is to use the information that is encoded during the encoding part, so here, to enrich information here. If you imagine the fact that we are actually doing a machine translation task, the idea is that I want to know that the meaning of the input sequence to be able to decode it in another language, right? So we want to pass this information between the encoder and the decoder. And so the idea is that if I then had here just using additional letter here, we have E and D that represents where they come from, the query, the key, and the values. In the cross-attention operation, what happens is that the key values, those key values, and the value vectors, key vectors and value vectors comes from the encoder. So they comes from the sequence that has been, so here we have these operations. Query, key, and values come from the same sequence. The idea is that those vectors are already computed, and we can use those vectors then in the decoder to compute the cross-attention mechanism. It means that the query, so how much attention and so on, so the query vector comes from the decoder, but the key and the values comes from the encoder. This is just to give some more information from the encoder to the decoder. Is it clear? Yeah? A question? Mm-hmm. Mm-hmm.
So the query from the decoder, I must have all possible words in English, and I have to find the query from all these words and use with the value and the key of the encoder and find
This is actually, I don't know how to translate the question for online, but the idea is that you're actually asking if, as input here, I can have the query vector for all the possible sequence of words, all possible words in the dictionary of English. Okay, so it's related to the input of the decoder, right? Okay, so the idea is that at the output of this stage, I have a vector representation for each word, right? Because it's, after the attention, I have a vector representation for each word. This becomes the input of the encoder, of the decoder, sorry. So I actually want to delete something here. Okay. So here I have my vector representations. This becomes, I'm sorry, I'm not good at drawing, but this becomes the input of this part. So they are like this is like this, right? I just draw one of this just because of the drawing, but this becomes the input of the decoder, and I apply the same thing. I decompose it into query, key, and values, and then I have all the operations, right?
And the decoder has different layers and vectors.
I have the composition is done on. I actually not sure if it's done on this using the same layers for the encoders or the decoders, but I have the same operation. So I map from vector to other three vectors. Yes. From the encoder to the decoder. Yes. So the idea is that these are the input of the encoder model. The output of the encoder is the input of the decoder model, but here I also pass from the encoder to the decoder the key and values. The query are coming from the input of the decoder. The key and the values comes from the encoder. Yes, question? Yeah, no, we use them. I actually, yes, this is the cross attention layer. Is it clear how it works? It's the same basic operation of the self-attention, but instead of using the key of the decoder and the value of the decoder, we just use the query of the decoder, and the key and the values comes from the encoder. Why we use them? Why we generate them? Because the idea is the question in the class was why we generate the value and the key vectors if we don't use them. We actually don't use them in this part because the encoder layer is composed of cross attention, that is the one that I presented you now, but we have also a self-attention layer. Actually, this is a masked self-attention. We'll see what is the difference. But the idea is that we also have as additional layer the cross-attention layer, the cross-attention operation. It's not that we just replace the operation of attention from self-attention to cross-attention. Is that we actually have an additional step of cross-attention to propagate some information from the encoder to the decoder. Is it clear? Okay. So we have this masked self-attention because the idea is that when we are decoding the sequence, we are generating the word one by one, right? So we are generating the first word, then we can pay attention for the second word just to the first word. For the third word, we can pay attention to the second and to the first word. So the idea is to have, if we have a sequence that we are generating, at each step, we can pay attention only to the words that we have already generated. This is why we call this masked self-attention, because we have self-attention component. It means that it's computed using the input of the decoder itself. So it's similar to the encoder self-attention. We have the input of the decoder, and we use the self-attention mechanism to compute the attention. But we have it masked. It means that at each operation, I cannot pay attention to all the words in the sequence, but I can only pay attention to the words that have already been generated. So I have an attention mask that is similar to the one reported here. So for the first word, they can pay attention only to the first word. For the second word, they can pay attention to the word itself and the one previous, the second. So for the third word, they can pay attention to the third, the second, and the first, and so on and so forth. Instead, for self-attention in the encoder, I have the whole sequence that is as input, and they can pay attention to all the words in the sequence because they are already generated. I'm not generating, I'm just analyzing those words. Is that clear? It's not very easy to understand, but please be sure that this is clear. So the idea is that here in the decoder, I have the masked multi-head attention. So it's the same operation, but instead of computing instead of computing these operations for all the words in the sequence, because I don't really have the other words because I'm generating those words, for the word 2, I'm paying attention to the word itself and the word before, that have already been generated. And this is why I have an attention mask that is similar to the one I have here. So it's a triangular matrix, actually, because I can only pay attention to the words that comes before and that I have already generated. Is it clear? If it's not clear, I don't know if there are questions online. No questions online? Okay. Okay, those are the basic blocks that we use both in the encoder and in the decoder. So they're actually the same operations. So the idea is that we compute the attention by the dot product between the multiple vectors and so on. And we have a different different proposition for the vectors for the cross attention. So they come from the encoder. And in the masked self-attention for the decoder, I can only pay attention to the left context, not to the right context, because I have not generated this. Yes. From the decoder, yeah.
I mean, can we do the mask?
Yes.
And the cross-attention?
No. In the cross attention, I use the same query. Yes, the query. Yes. Yeah, we use the same query because they all come from the decoder. Yes. Okay. Is it clear? Okay. So if it's clear, those are the most important part for the transformer architectures. But if you analyze these operations, the fact that I compute the attention between each word and all the others, if I shuffle the words in the sequence, I will have actually the exact same representations, because they are actually not dependent from the position of the word in the sequence. So I can have the pen is on the table, or the table is on the pen. If we have the same set of words, for each word we have the same representation. So to avoid this issue in the sequence, because in the sequence we need to take care about the position of the words, we use positional encoding. That is a trick, actually, to encode the position of the word in the sequence by using what we use here is an additional vector. So we have an additional vector. We have all the attention and so on and so forth. It's the same, but we use an additional vector that is actually added at the beginning of the sequence. Here we have the positional encoding. So we have the embedding, we add the positional encoding, and then we do all these our operations. The idea is that we use this positional encoding to encode the information that the first word is the first in the sequence, the second is the second, the third is the third, and so on and so forth. We can do this by just encoding the information about the order, so 1, 2, 3, 4, and so but it's actually not efficient and not actually the best solution. What happens is that we have a vector that is a composition of different sine and cosine waves that use actually different frequencies. And this is similar to the one that you have here. We have different sine and cosine. They goes from 0 to 1 with different frequencies. And the idea is that for a given word, I have, for the first word, I have all these values from different sine and cosine waves. And so I encode this information in a vector. So this is the first word. This is the vector of the first word. The second word perhaps should be here. So I take all these values from different sine and cosine waves, and I compute the second positional encoding for the second word. And the idea is that using sine and cosine, I can encode information about different frequencies. It means that if I use a reasonably high number of sine and cosine waves, I can actually encode each position in a different vector, because at least one of the component of one of the cosine and the cosine, one of the sine or cosine waves will differ of a given value, because I'm using different sine and cosine waves. The second thing is that each sine and cosine, each wave here is encoding a local distance between these words. So if I have this first wave between the first and the second one, there will be a difference of values that is actually encoding how far they are in the sequence. Is it clear? No? I don't know if I can actually go here in this link. I don't think. What I want to show you is that using the sine and cosine waves at different frequencies, I can actually encode the information about the locality in a given cell. So let's consider we have a single sine wave. This corresponds to a single cell in our vector, because we have a vector of different elements, and each sine wave is giving the element for the first one, for the second one, like always for the first element in the sequence in the vector, but taking in account the fact that this is the first element in the sequence, this is the third one, this is the fourth one, and so on. So we have, for example, here I have 0.0 for the first element in the sequence. For the second element, this is W1, word 1, and this is word 2. The idea is that this sine wave, I want to use different colors actually, because I want to show. What? We have a value from the sine wave for each word. So we have the sine wave here that has a given frequency, and then we have, this is the value for word 1, this is the value for the second word, this is the value for the third word, right? So we have this one correspond, then we have for the word 1, word 2, and word 3, we have a vector representation. And the first cell in this vector is given by this sine wave. Then we have another sine wave that can have a different frequency, and we have the same spacing between them. So we have this, 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 and this. And the second element will be part of this sine wave. So for each different sine wave that we have a different position in the positional encoding vector. Exactly, we have as many waves, sine and cosine, a combination of them, for as number of elements in the positional encoding vector. Is it clear? So we have a combination of different sine and cosine waves, and we use the same spacing to compute actually the values that will be part of the positional encoding of each word. So if we have, these are actually the encoding by using the colors of the values for different sine and cosine, we can see that they have different frequencies because they actually have different bands of colors. And the idea is that for the first position, for the first position in the sequence, we have it's not, but it's like taking a part of this, and this will be the positional encoding for the first word. Then, of course, this is just, I'm taking a lot of them, but it's actually having a single value here. But so we slice this matrix using horizontal splits to have the positional encoding of the word W1, W2, and W3. Yes, question. Why not 1, 2, 3, 4? Yes, this is a very, 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 very good question, because proceeding in this way, we can encode local and global information. So to let you understand this, I want to delete everything here. I can, okay. So if I have this sine wave, and then I have this sine wave, so I have sine waves that have different frequencies. If I use the same spacing for taking the values, the idea is that here I have same spacing. The idea is that if I have just 1, 2, 3, 4, I can say that the 10th word is distant 6 from the 4th word, right? But if I encode the information like this, I can encode local information, local distance in some cells of the positional encoding, and global or like less local information using sine waves with having like lower frequency, so a very high period, right? So if I have a very long, a very low frequency, so a very high period, the elements in the sequences will have very close numbers, right? Because I'm using actually different. I'm using a sine wave with a very high period and a very low frequency. So the idea is that I don't know if the network need this information, like about the locality and the globality of the how distant words are, but I give this information to the network, and during the training it will learn if they need to have, like, if the network and to perform my my task at the end, it will learn how important is different different part of the positional encoding vector, or different part of the it can happen that the position is not relevant for my task. It will learn to discard positional information. But if it's important that after the dot, I'm referring to he, because here was like Moreno at a certain point, was my name, I'm a male. If I'm using he, it's important to know that if it's like 20 words after, it's referring, using this kind of encoding global and local, I can actually have the information that those two words can be connected. So the network will learn how to exploit this information. Instead, if I just give the information about 0, 1, 2, 3, 4, it will be not possible to encode some, I don't know how to say, but some periodical information that, like, here I have the same value for this. If I use a lot of waves, I can have, again, the same value after a certain point, and this can be exploited by the network. Is it clear? Okay, can you explain which are the vectors from the encoder and which from the decoder? I think it was a question from the previous part. Is it related to this part, to the cross attention for the online people? Was a question, can you re-explain which are the vectors from the encoder and which from the decoder? It's referred to this. If it's referred to this image, the idea is that all the vectors that have E as predix here will be part of the encoder, so they come from the encoder. The one with the D, they come from the decoder. It means that the query vectors come from the decoder. Instead, the value and key comes from the encoder. No, it's not a fault. Okay. Is it clear? Yes. Okay. I think we can go on. I think with positional encoding, we actually finished the most theoretical part and the most difficult part. The idea is that positional encoding use waves like sine and cosine to encode global and local information instead of encoding just 0, 1, 2, 3, like just this discrete position in the sequence. And the self-attention mechanism is actually, if you understood the basic operations for the self-attention, it's applied in the exact same way, but using key and values from the encoder for the cross attention. And for the masked self-attention, it's actually the same exact operation as self-attention, but is applied by just paying attention to the left context, because it's the only one that we have already generated using the encoder, using the decoder. So if this is clear, I actually put here a link. This link is pointing to more detailed explanation of positional encoding. You can just try to see the values of the positional encoding using different numbers of waves, and you can better understand how positional encoding works. I suggest you to see this demo. It's an interactive demo of the positional encoder. Yes? Yeah. Yes, in the sentence. If I have the pen is on, so on and so forth. Local information is that if I have a high frequency wave, I will have the same or similar values for words that are near. Instead, if I have a very high period, like very low frequency wave, I have a more global, it's not global, but it's more dilated in the space, in the time information about the locality of words. So perhaps there is on the, so this word and this word will have similar, it's not semantic, it's like encoding different kind of information with different frequency for the waves. And so I can encode local information, more local information if I use high frequency waves, and more global or less local information if I use waves with lower frequency. Is it clear? Okay, so with that, we have concluded the part related to the theoretical part of positional encoding. Yes, positional encoding and all the others information about the the theoretical part of the transformers. The idea is that we can build encoder models, so models that take the inputs take as input a sequence and perform discriminative tasks. So, for example, classification. We can build decoder models that just produce text. With a given prompt, they just continue your text. And we can learn sequence-to-sequence models that are similar to the original transformers that learns how to pass from a given sequence to another sequence. In the case of the transformers, for the machine translation task, we pass from a sequence in a given language to a sequence in another language. So the first, not the first, but one of the first models that use transformers for having an encoder-based model is BERT. You have seen this with Professor Cagliero. The idea is that we have an encoder-based model. We have different encoder layers stacked one after the other that analyze the input sequence and generates a vector representation for each token in the sequence. We can stack actually multiple multiple encoder layers. For example, we have 12 transformer blocks with 12 encoder layers for the BERT-based model. And we can learn those models using self-supervised learning and using a specific self-supervised learning task. The idea is that BERT uses two tasks to leverage normal text. The first one is masked language modeling. The idea is that I want to have, in self-supervised learning, similar to Word2Vec or the other architecture that we have already seen, I want to leverage not annotated text, so I don't need annotation for this text. And I usually, in self-supervised learning, I build a task to use free text from the internet or from Wikipedia, from books, and so on and so forth. The first task used by BERT is masked language modeling, where the idea is that I have a sequence of, I have a sentence. I randomly mask the 15% of the word of the tokens in the sequence, and I learn to reconstruct. I learn to predict which is the correct word that I have masked as an input. So I have, this is a pre-training strategy. I mask pre-training, and so the input of the model is, this is a mask strategy. So I replaced the pre-training, the word pre-training with mask, that is a masking token. And the model is trained to predict that instead of mask, I should have pre-training. So you can imagine that you can create a lot of training data by just using this trick. And the idea is that the model should be able to predict which is this word given all the context around it, right? Similar to Word2Vec, but in a more powerful way. So this is the first pre-training strategy. BERT uses two pre-training strategies. This is the first one. So randomly masking 15% of the tokens with always with the same token, mask. And the idea is to predict which is the word that I masked. Is it clear? All of you? Okay, so this is the first task, that is masked language modeling. And the second task instead is next sentence prediction, where I have the text that I have is decomposed into sequences, like sentences. So I can just split by using the full stop. And the idea is that I build training data by just using one sentence and its next one as an example for training. And for the same sentence and a randomly chosen one from the rest of the corpus as a training example. So we use the first one as a positive training example. So it learns, for example, here I have BERT is a model. It uses deep learning the model should predict if the second sentence follows the first. So here, BERT is a model. It uses deep learning. It's actually true because it can happen that the second sentence, so it uses deep learning, is following the first one. BERT is a model. Instead, the negative example here is the fact that BERT is a model, and I randomly sample a sequence from the corpus. So today is sunny, but it's actually not related to the original sentence, and so the model should predict false. So the first is a positive example, and the model should predict true, and the second one is a negative example, and the model should predict false. So the idea is that by using the first and the second pre-training tasks, the model will learn first to understand how the words are placed in the sequence, and second, to have some logics about the first sentence following the second one. And as you can imagine, by using these simple tricks, so by just replacing some tokens with mask and just sampling random sentences in the sequence, in the corpus, to create positive and negative examples, I can have thousands and millions actually of training examples, and I can use all these examples to train my transformer models. It's actually, this step is called pre-training. It means that it's independent from the task itself that I will do at the end. See if I can do the sequence classification, I can do token classification, it doesn't matter. The idea is that I do this very costly pre-training step only once, and then I take the pre-trained model and fine-tune the model on a specific task. That can be sequence classification, token classification, name identity recognition. It doesn't matter. The idea is that this pre-training phase is always the same. An evolution of the original BERT model is RoBERTa. It's actually the same exact model of BERT. They only change some hyperparameters, so the dimension of the model, the dimension of some vectors, and so on. But they usually, they actually propose dynamic masking. So the masked language modeling that I proposed here was done once for BERT. During the training of BERT was done only once during the pre-processing of the text. The idea is that if I do this dynamically during training, I mask different words instead of always masking the same words from the same sequence. I actually can learn better a representation for those words. But it's actually a very minor evolution of the original BERT model. And so these are encoder-based models. It means that they not produce text. They just analyze the input sequence and can perform discriminative tasks, such as sequence classification, token classification. So for example, sentiment analysis, I can identify the emotion in the text as being a positive or a negative emotion, but they actually do not generate new text. Instead, we have the opposite part, so using only the decoder part of the transformer architecture. And the idea is that I always want to use self-supervised pre-training because those models are very data hungry. That means that they need a lot of data to be effectively trained. And the idea is that those models are trained to generate text. So the very basic pre-training strategy is the one used by those models. We have text. We just give the first few words, and we need to predict the next word. So I use this is a pre-training. As input, the model should output the word strategy. So the idea is that it's able to predict, it assigns a probability of having as next word that one to all the words in the vocabulary, and the idea is to maximize the correct word during the pre-training phase. So the idea is that we have text, we input a prefix, and then it predicts the next word. And the backpropagation happens when we have the correct word that is in the sequence, and we maximize this probability given the prefix words. So it's like just next word prediction as a strategy, because we just predict the next word, and we can just use all the text that is available online to train those models, because it doesn't need to have any annotation, similarly to the BERT model. And finally, we have encoder-decoder models like transformers. But another model that has gained a lot of attention is BART. That is actually an encoder-decoder architecture, usually called also sequence-to-sequence model. And it uses self-supervised training also, because it needs to be trained with a lot of data. And the idea is that in BART, I want to corrupt text, so alter the text that I have as input and reconstruct the original text in the output. I have a lot of examples here. So we have different examples for corruption. The first corruption that I can apply is sentence permutation, where I have the original document is always on the left. The output of the expected from the model is always on the right. And on the middle, I have the input of the model. So the model is here, BART is here. This is a preprocessing operation. So I apply preprocessing, and in the case of sentence permutation, I have different sentences in the document. I split the document into sentences. I randomly order them in to create the new input example. So I have A, B, C, D as sequences, as sentences. I just produce an altered version of this by using D, A, B, C, and the model should be able to produce again A, B, C, D. So putting the sentences in the same order. Then I have token infilling. I just randomly mask one or more tokens, actually more than one tokens, using the mask token. So I have 1, 2, 3, 4, 5, 6, 7, and 8. I just sampled these 3, so 2, 3, and 4. I mask them. This is the input of the model. 1, mask, 5, 6, 7, 8. The model should be able to reconstruct the sequence, and so to place 2, 3, and 4 here. So this is token infilling. Then I have token masking. So it's the same of token infilling, by just masking one single token. So it's similar to masked language modeling, but in masked language modeling, I predict which is the sentence, which is the token that I masked. The idea here is that I have a sequence-to-sequence model, and if I put this as input, it should produce this as output. So the whole sequence, and here should place the correct 4 in the correct place. Then I have token deletion, where I just remove one token. Here the 4th token has been removed. So I have 1, 2, 3, 5, 6, 7, 8. I should be able to predict the sequence, the correct sequence, and so to identify the fact that here is missing the 4, and I predict the 4. And finally, I have document rotation, where I have I randomly choose one token. In this case, it's the 7, and I rotate the document to start from that token. So if I identify 7, I have 7, 8. Then I have 1, 2, 3, 4, 5, 6, and the model should be able to predict the original document. So to re-rotate the document. So these are different tasks that are used to train the BART models. And these pre-training tasks are similar to perhaps some other tasks. And the idea is that it gives you the model the understanding to reconstruct the original document. So it gives the model some information about the understanding of the English language. And so what happens is that using these sequence-to-sequence models, so we have an encoder, we have a decoder. The encoder is similar to BERT. The decoder is similar to GPT, so the decoder model that we have seen in the previous slides. and we can perform different sequence-to-sequence operations and tasks, such as machine translation, so from one language to another, or text summarization, for example, summarizing a document to a shorter version that convey the same information but shorter. Okay, do you have question on this part? Okay, so it covers this first part covers the overview of the transformers architecture. I hope this has been useful. We can go on with some exercises about the transformers. What I want to point out here is that in the remaining part of the labs, we will use Hugging Face transformers as a library. In the next lab, we will do a brief introduction of the transformer library, just to let you make you familiar with the most relevant concepts of this library. This is a very powerful library. This is actually very, very used in the field of NLP. This library, yes, it's named after the model itself, so the transformer. So it actually includes a lot of pre-trained models that we can use. We can use the code that they provide to do some fine-tuning. So it's very handy, and we will use them in the next labs. We have a lot of models that are already available. And the idea is that, yeah, here I have just another remark on the fact that we use the self-supervised learning to pre-train those models. Those models are available on some repositories, such as on Hugging Face transformers, and then we can fine-tune those models on a specific task. The idea of self-supervised learning is that we can define a proxy loss. It means that we have a task with a given loss that is able to make the model general and generalizable to different downstream tasks, also to perform different tasks. And the idea is that it can learn semantic representations. So BART or BERT to predict whether a given word is placed instead of mask should have an understanding of how English is composed in text. So the idea is to learn those representations that are semantically aware, and then we can use those words, those representations to perform different tasks. Here I have a few exercises just to give you an idea of what can be the exercises on the exam, or some exercises to let you understand if you understood the most relevant part. The first one is given a random initialized BERT model, so no pre-training yet. Illustrates an example of the self-supervised procedure to pre-train the model using masked language modeling. So you should be able to understand how masked language modeling works, and you should provide an example for the input and the output of the model. So here I have the procedure. The input is the model and a list of sentences. The idea is that for each sentence, it generates masked sentences, and for each sentence, I mask P% of tokens, where P in BERT was like 15%, but I can choose another one as a value. So I have this training example. The mask is on the mask. So I mask pen and table. The idea is that I have as input this for the model, and the output is this one. So I should predict pen and table. And so for each sentence in the list, I forward pass the probability for each masked token. I compute the loss, backpropagate, and train the model. If I want to do a pseudocode version of this, I have for each sentence, I produce a tokenized version. I mask this, so I can think about having a function that masks a given tokenized version of the sentence with a probability, with a given probability. And so I have sentence that is the pen is on the table. The masked text is the mask is on the mask. In this case, I have a mapping in the tokens, and for example, the mask token here is 100, and so I have this vectors. I can forward pass them to the model, the masked version. I can compute the loss between the prediction and the sentence itself, and then I can use backward to train the model for each sentence in the list. Yes, another example, the same as before, but using next sentence prediction. Here, instead of model, I have instead of the list of sentences, I have a document. This is a list of sentences, because I should sample negative examples from other documents in the corpus. So the idea is very similar. I generate the training set. For each sentence, I create a positive pair, and for each sentence, I also create a negative pair. So one positive and one negative. An example of the training here: Polito is a university. Sentence 2 is it's located in Turin. So this is a positive example, output 1. Instead, I have a negative example: Polito is a university. Next season is coming. So it's completely unrelated to the previous section sentence. So the idea is that he should be associated with the label 0. And so I can use the classification objective. And so I can give them as sequences to the model, and then the model should be able to predict 1. And so I can forward pass to the model, backpropagate by having the correct label. Okay, by using pseudocode, it's very similar. So I have for each document in the documents, I have for each sentence in the document, I have positive pairs, and I can construct the positive pair as a sentence. It's following 1, and the label is 1. And the negative example in this case is a random sample of the documents. I choose a random sentence, and so I have the sentence, the negative examples, and the associated label that is 0. Then again, I forward pass to the model, compute the loss backward on the model itself. Yes, here I have another bonus exercise. It's actually the code to pre-train a given model by using the transformer library. It's actually the we can just comment a little bit the code. The idea is that we need to first learn a tokenizer that is able to map a sequence of words into a sequence of tokens. Yes, we have the code used to train a tokenizer, and we can save the tokenizer. So the tokenizer is able to split sequences into subtokens. So we have subwords, so tokens. We have here we can specify a given vocabulary size, the minimum frequency for each token, and some special token that we can then use for our fine-tuning tasks. So first we train this tokenizer. We will have the overview of tokenizers, models, and so on with the code on the next lab, that is next Tuesday. So the idea is then we create a class called dataset that is able to process all the text to create this sequence of tokens. And then we have the getItem function that gives me the example that I can use for training. Finally, yes, in Hugging Face, we have already pre-trained, prepared scripts that we can use to train those models by just giving our tokenizer here, our configuration, our name for the model, and some hyperparameters that we want to use to train our model. So the idea is that you have a Swiss knife that you can use to perform different, actually, tasks using transformer models. Yes, here I have another example for the semantic search engine, something that you have already seen yesterday in the lab. So the idea is that if I have as an input sequence of a list of sentences or a list of documents, the idea is that I want to build a semantic search engine that can use BERT to represent the documents and the query, and can perform similarity operation between the query, the input of the user, and the sentences that I have in the input corpus. I will just, okay. So the idea is that in BERT, I have a single vector for each token. Instead, what I want is a fixed representation for the whole document or for the whole sequence. So the first thing I should do is to define a pooling function. So a function that aggregates multiple vectors to give me a single vector representation for the whole sentence. So I have this pooling function. We can use the average, the minimum, and the maximum of those vectors. We have an alternative. We can also use a specific token to encode the information about the whole document. We will see more on this in the next slides. And for each sentence, the idea is that we can forward pass it to the model and use the output of the model as a sequence, as a vector representation for the document, and we can index those vectors in Apache Solr or Elasticsearch, that are some software used for information retrieval and for building search engines. So here I have you have the pseudocode. It's similar to the one that you have already seen. And here I want just to point out, one of the libraries that you used yesterday, that is Sentence Transformers. Actually, this is a library intended to map a given sentence to a given vector. So the idea is that it uses, under the hood, it uses BERT-based models to map a given sentence to a vector, and this vector can be used to index those sentences in a search engine, and then we can perform information retrieval by using those models, and we can so use semantic information to do information retrieval. Okay, I think we can stop now for 15 minutes. And we can restart in 15 minutes with some additional things about the lab of yesterday, and we will discuss the solution together. Okay, there is just a question online. Are the BART corruption steps applied in combination, like rotation and deleting? So this is a question online. The answer is no. They are applied not simultaneously. It means that I can apply just one of the tasks to the input sequence, not multiple of them at once. Is it clear? Yes. Okay. Any other questions? Okay, so 15 minutes of break, and then we will start again. I also restart the recording. Just a question online. Next week, there will be the lab. So next week, on Thursday, we have the lab. We had the lab yesterday. I will discuss about the lab of yesterday in a few slides. We will discuss the solution. But yes, for the question, yes, we have the lab next week. Okay, I think we can restart. So yesterday we had the lab about information retrieval, PageRank, and recommendation systems. It was a very long lab, actually. I know that most of you, we were not a lot on the lab yesterday, but I think most of you did not succeed at finishing the lab. That's perfectly normal. I want just to discuss with you the solutions of the lab, because if you have questions, we can take this time to discuss those questions. For those of you that already solved most of the lab, please be patient. We will discuss, and if you have question, even if you finish the lab, we can discuss it. Okay, so in the yesterday lab, we introduced the concept of PageRank, and the idea was to create, the first questions were to create a graph of articles from Wikipedia, to connect them in a graph, and to compute the PageRank of each Wikipedia page. So the question number 1 was exploiting the Wikipedia citation network computes for each page its associated PageRank score. And then the question was, what is the page with the highest PageRank score? So here we have the solution. The idea is that we use NetworkX. We use NetworkX as a library to construct this edge. We have a dictionary of articles. We have at the inside this dictionary, we have multiple web pages. The idea is to use the outlinks information to create this graph. So in this specific version of the solution, what we had is a list of edges and a list of arcs. So the idea is that we can use these lists to create our directed graph here. So we had the nodes, we had the edges, and we then can compute the PageRank algorithm by just using the PageRank function by NetworkX, and then we can print the best, like the web page with the highest PageRank score by just sorting this dictionary. Do you have a question on the first? On the first part? Okay, so I think most of you did this part. So okay, the second and third question were about creating actually a semantic search, a search engine by using these Wikipedia pages. You should be able to access the full text of each page by using a specific folder that they put, like I downloaded on Google Colab. And so the idea is that you use the specific version of the ID of the page to access this information, and then you can index it on Elasticsearch, and you can query Elasticsearch by using the interface given by the Elasticsearch by library. An example for the query was the capital of Italy, and then you should be able to get the results. So the idea is that in the first part, you should be able to read the documents. So for each item in the dictionary, you should be able to access the full text of the article in this way. And so you can read this document. You can then enrich the original dictionary by using the PageRank score and the full text that you parse in this way. And then you have the dictionary of articles, and then you can just call the es.index function in Elasticsearch to index the Wikipedia articles. Then to answer the third question, you should be able to construct a body containing a query. It means that you should follow the rules of Elasticsearch to construct a dictionary, a specific dictionary, where we have the field query, then match, and then the field that you want to query on. In this case was full text, and then the query you want to enter, and then you can print the results. It seems easy from here, but it's not. Do you have a question on this for those of you that were yesterday on the lab? Even for those of you that were not on the lab, if you have tried? Okay, but here you have like the solutions and the ideas that you should use. Here, for example, there are some details. You can import the Elasticsearch library. You can create your index by using the create function. If you go on the homepage of the documentation of Elasticsearch, you actually have very similar code that you can use to create your own solution. The fourth question was to integrate the PageRank scores in Elasticsearch. It means that when you compute the score to retrieve the most pertinent document, you should take into account the PageRank score of the page to compute a custom score that is hybrid between the score given by syntactic match, that is the official score by Elasticsearch, and the PageRank score that you computed, scaled by a factor of 250. Okay, yeah, that was the question. If you perform the same operation, does it change the results? Yes, the order actually changes. In that case, we have a search term that is the capital of Italy. We can create a custom query request that actually was linked. The template for this was linked on the Google Colab. The idea is to use a custom script score where you actually write a custom, very custom script. It's not a script; it's very one line of code. When you actually, if you have the PageRank score for the result given by Elasticsearch, use this PageRank score multiplied by 250 to rescale the pertinence of the document, and so to reorder the results. For those of you that are asking, those solution will be, of course, uploaded not only by means of the slide, but all the notebook will be uploaded on the didactic portal. So no problem with that. The same here. This is a visualization part where we search by using this body as a query, and we print out the solution, actually the retrieved documents by Elasticsearch. So the difficulty here was to integrate the PageRank score into a custom scoring function. Do you have a question on this? Okay. If you don't have a question, we can go to the question number 5 that actually extends over again and aims at creating a new index that was the wiki semantic search, where we encode with the full text. We also encode a semantic vector that is given by sentence BERT. So the idea is that for each document that we have, we put this document as input of a model, and then we get a semantic representation of this text, and this is encoded in a vector, and this vector will be put in Elasticsearch, and then we can use this vector representation during query time to compute the semantic similarity other than the syntactic similarity. So here the things are a little bit trickier, but the idea is that first I need to, I think the orange is is visible in both cases. So I instantiate a model for each text. For each full text, I get the list of text and I encode them. Why I did this instead of doing for each document I encode separately with different calls. The idea is that if I perform the operation in this way, so with a list of text, it will automatically batch the documents, and so it will be faster. But it's a matter of speed. So if you did it like for each document index, like encode this, it will be the same. Then once we have the sentence encodings, I enrich the dictionary information with this embedding BERT, and so we at the end we actually have the vector of each document as a part of the dictionary itself. Then this part was provided in the lab. The idea was to create a custom index. In the first case, I did not create an index customly, just because all the documents, all the fields belongs to standard types. So they were like strings or floats. Sorry. So in this case, instead, the idea is that I have a dense vector, and to do this, I need to define a custom index. So I need to provide some additional information for the index. So here, I provide a specific dictionary for the properties of the index. The idea is that for each field, so ID, quoted ID, full text, I have its type. The same for the PageRank score, that is a float, and for the embedding BERT, that is the vector, I have the type dense vector, and I specify also the dimension of this vector. Okay, what was the question? Oh yeah, the idea is that the next part, the part of the indexing, is always the same. I iterate over the documents. Is similar to this part. So I iterate over the documents and I index each time all the dictionary representing the document. In this last case, in addition to all the other things, I also have embedding BERT, that is the semantic vector representation. Going on, after information retrieval, the idea was to use Elasticsearch to build a recommendation system. It's a very basic recommendation system because it takes only into account the fact that you have seen a given movie, and so with a given plot, to search for similar movies. So the idea here is to use, again, sentence BERT to encode movie plots into fixed size vectors, and then we use this information to query by giving the name of a movie that I have seen. Okay. So the idea here is always the same. I instantiate the document. I have a list of plots, title, and a list of embeddings. So here the list of embeddings is given by encoding all the plots, and I can then index them on Elasticsearch, and I can create my index, Praxis movies, and I can index those documents. Once the documents, so the information about the movies are indexed, the idea is that we can query. First we can index those documents. So we can iterate of the documents, create a document, and index it on Elasticsearch. And then the idea was to query the document, query the search engine. In this case, it's like a recommendation system by using one of the titles of the movies. So the idea is that you provide a title, you get the plot of this movie, you encode it. So the idea is to get title. Sorry, the plot. You provide a title, so you get the plot, encode it, get the semantic vector, and use this vector to perform the query. So how it works? So you have a function that is called encode plot that given a title, a movie title, and an embedding model, and the data frame containing the information, it takes the plot of this movie. So here the plot, get the plot vector, and returns the vector representation of the plot for this movie. And then we can use actually the same functions that we use to compute the semantic similarity here, so cosine similarity between the query vector and embedding BERT, to compute the semantic similarity between the query and each movie in the database, and then we can print out the results. Here I remember you that because we change the script that is used to compute the score, here the score will be the semantic similarity between the cosine similarity actually between the query vector and the vector of each document. Okay, there was a bonus question. If I read, if I've seen multiple movies, I can actually get the plot of each of the movies that I've seen, and then I can aggregate them by using the average, actually the mean function, and to compute from, we can pass from multiple vectors to one single vector here, and this will be my query. So my query is not now the embedding of a given plot, but is the average of the semantic representation of multiple plots. And so if I do this, I can actually use this new query vector to create my script to compute the semantic similarity by using this vector, that is the input of the movie, the input of the information retrieval system, the search engine, and then I can search for movies that are most similar to this average embedding vector, and then I can print out the results. Okay, the break was actually after the this part. Do you have question on this? I think most of you had not the opportunity to do the lab. So if you have questions after you try to do the lab at home, I don't know, if you want to ask questions, please, you have the Discord channel, the Discord server. You also have my email address. Please ask, because I know that can be frustrating to do not have answers for some questions. So please ask, don't be afraid to ask, no problem. Okay, so we already did the break. So the idea is that we can now continue with some exercises and some introduction to the details of some task-specific transformers. So we have seen how, you have seen also with Professor Cagliero how the attention works. We have seen today at the beginning of the lesson how attention works. The idea is that how we can use these very powerful models to perform some specific tasks. So I want to just identify the emotion of a given sentence. So I like this movie. So it's a positive emotion. I want to identify this sentiment, this emotion in the sequence. So I want to perform sequence classification. How can I do? We will see how we can do this. So recap, but we have seen this like a few slides ago. In large language models like BERT, the idea is that we do a pre-training phase by using self-supervised learning with masked language model, next sentence prediction, and so on. So we do this pre-training phase, and then we take this model and we fine-tune for a specific task. So self-supervised learning is applied on standard pre-training tasks, such as masked language modeling, and we do a step of supervised fine-tuning with just a few labeled data. So we have a lot of training data for the pre-training phase, because we can use all the text that we have. And then we can fine-tune the model using self-supervised learning with sequence labels. So we need the labels associated by humans or in some way associated by someone. And so we need to have supervised data. Sequence classification. So the task of sequence classification is, given a text sequence, a sentence, or a paragraph, we want to associate a class to the given sequence. Sentiment analysis is a sequence classification task. We want to identify if a sequence has a positive, a negative, or a neutral sentiment. So this was a good movie is a positive sentiment. It was an average experience. It's a neutral sentiment, I should say. And then we have, I hated that, so boring. This is a negative sentiment, right? Similarly, we can have similar tasks such as text categorization. If we have a sentence, we want to categorize them. We could categorize it as belonging to a given category. So the team won the match. This is sport. Joe Biden was elected as US president. This is politics or like elections. And then we have Google stocks went up. So this is something related to finance. If we want to perform this kind of tasks, we can use BERT models. So we don't need to produce new text. So we don't need decoder models. We don't need sequence-to-sequence models. We can use encoder-based models such as BERT to perform those tasks. And the idea is that we have this kind of architectures. So we have BERT. The input of BERT is a sequence. So we have the text of the sequence. We add some specific tokens at the beginning and at the end of the section of the sentence. So we have a CLS token, and we had the separator token at the end. We use some tokenizer to tokenize the sentence into tokens. So we have this visually stunning rumination on love. I think this is this is the sentence. So we first tokenize it. We then pass from the token to its ID by using the tokenizer. And then we can pass this information to the model. The model processes all this information and give us the outputs. And each vector in BERT-based architecture, each vector for each token is has a length of 768. So this is the hyperparameter used to train the original BERT model, and this is what we have as pre-trained model of BERT. What we can do, I said you that we had a special CLS token and a special separator token. The separator token is not necessary for our cases, but the classification token is usually useful to perform sequence classification, because one way to act is that we can use this special token, because it's a special token, but it goes into the model similarly to all the others. So we have the model output for this CLS token, and we can use this vector. So for the first token, as a feature encoder that encodes all the information for the whole sentence. So during training, if we use this vector to perform classification, the idea is that it will learn, the model will learn to encode most of the information about the sentence in this CLS token, and so in the vector representation of the CLS token. So here you have the way to access this information. So you take the last hidden state, so the last layer of the transformer model, and you take the first element. So you have all the sentences, you have only the first position, so the CLS token, and you take all the 768 hidden outputs. So you take here, if you have multiple sentences, you put all the sentences on the model, and you take for all the sentences only the first one, and you take all the dimensions, so 768. And you have at the end, you have vector representation of 768 for each sentence that you put as input on the model. So here again, you have this vector representation from 0 to 768 for all the sentences, all the sequences that you had. The idea is that if you do in this way, you can use BERT as a feature encoder. So you use this model as an encoder model to produce these vector representations, and then you can build a classifier on top of these these vectors. Yes, so it's like feature engineering. So I'm extracting the features from the sentences. So you have a matrix where each sentence is mapped to a vector of 768 tokens. So in this case, it's 767 because it starts from 0. And you have the label. So you have vector and then the label for each example in the dataset. So the idea is that you can proceed by just extracting this information by using BERT. You extract all this information, and then the output. So you have this big dataset with the vectors and the labels, and then you can apply some machine learning classifiers such as logistic regression that take as input the feature representation given by BERT and output the class label. So in this specific case, you are using another model. You are training another model on sentence embeddings produced by BERT. So the idea is that you use BERT to extract features, and then those features are used as an input to another model. So BERT in this case is not trained, so you don't need to have big computational resources to train BERT, so it's more efficient. But you only train a logistic regression model. So a very shallow model, so inexpensive. But actually this approach is not very effective, because actually here you are not modifying the weights of BERT that are able to encode semantic information, and so you are not exploiting the full potential of BERT model. The second way of proceeding is actually to have an additional layer after the BERT model that is actually a dense layer. You can use one layer of neural network, and this layer acts as a classifier, so it outputs a label. And actually what you can do, yes, it can be a dense layer with a rel activation function, for example. This is called a classification head because it is an head on top of the big BERT model. And the idea is that if you have your training data, you can pass them through the BERT model. You can have this representation, so the classification token representation, similarly to the previous case. You can pass it to the dense layer. You can compute the loss given the correct label, and you can then backpropagate. But you are backpropagating not only through the dense layer, you are backpropagating to the whole BERT architecture. So the idea is that if you proceed in this way, you are changing those weights. You are changing the encoding. You are changing the encoding produced by BERT, and so in this case it's less efficient because each time you need to backpropagate and update the weights of the whole architecture, but is more effective because the architecture learns how to produce effective representations for those kind of sentences and for this task that you are performing now. So the idea is that, okay, it gives you averagely good representation for the sentence, but if you fine-tune the whole network for your task, it will be more effective than just taking this as a feature encoder and learn only a shallow network on top. Is it clear the difference between them? For all of you? Okay. So this is the differences. These are the differences between the two approaches to perform sequence classification. Here I reported you some code examples for the sequence classification task by using Hugging Face transformers. You can instantiate your model by just calling by just instantiating those two classes, so auto model for sequence classification and auto tokenizer. The auto classes are the classes that automatically infer which is the model. So you have the BERT model for sequence classification, you have the Roberta model for sequence classification. If you use auto model, they will just use this tag to detect if this is a BERT model or if it's a Roberta model, and so on and so forth. So you instantiate those two classes and then use the from pre-trained function to instantiate your tokenizer and your classifier. So then you can pre-process your data. You can apply the tokenization part to the trained sentences, test sentences, validation sentences. You can then create your own class that is able to encode all this information. So you have the encodings and the labels. So the encodings are given by the tokenizer. You have the labels that are in the data collection. And in the getItem function, the getItem function is the function that is called each time we call, for example, if I call dataset 0, for dataset, it will be called this get item function with index 0. So this is just a getter function to get a specific element in the sequence. So I can write my get item function to get all the items in these encodings. These are the information returned by the tokenizer. And so, yeah, I can just create those data sets, and then I can use a trainer that is actually a class introduced in Transformers that is able to actually abstract the training procedure. I don't need to write my training loop to use the trainer. I just use the trainer, and with some hyperparameters, it takes in charge the training of my sequence classification model in this case. So I can define my batch size for the training set, for the evaluation set. I can define the number of epochs, when I want to store my results, and then I can just train my model with a few calls on specific functions. So please take into account this part of the code, because it will be useful in the next labs. The sequence classification, the sequence classification task that we have seen is to take a sentence, so multiple words, multiple words. So we have a sentence with multiple words and an associated label. The idea is that we can also try to perform some token level. I don't know why. Okay. We can also perform some token level tasks, such as entity recognition. You have seen entity recognition with Professor Cagliero. The idea is to recognize entities in the text. So if I have free text, such as the one that is reported here, the Polytechnic University of Turin is a public university based in Turin, Italy, established in 1859. It is Italy's oldest technical university, and so on and so forth. So if I use a named entity recognizer, the idea is that I identify some geopolitical entities, such as Italy or Turin. So they are cities, or they are locations. Identify organization, here the Polytechnic University of Turin. A date, 1859, here again Italy. So the idea is to identify something that relates to a given concept. So a date related to the concept of 1859. The Polytechnic University of Turin is referring to our university. Turin is referring to the city of Turin, so it's a location. And the idea is that I want to classify each token, so each word or each token in the sentence, to be part of one of the classes. And if we define the kind of classes that we can define, we have the no entity class. So is a public, is not a specific entity. And then we have, for each entity, we can define the word that marks the beginning of the entity, and all the other words that are inside the entity itself. So if we, for example, here in the first sentence, I have the Polytechnic University of Turin is a public university. So I have all this that is an organization. So the Polytechnic University of Turin. The idea is that I have for the class is beginning of organization, and for all the other words that are inside the entity, I have inside organization. So we have a different class that marks the continuation of the entity in the text. So the task of entity recognition is a token level class task. So it's a task that does not classify a sequence, but classify a single token. We can define several classes. We can define location, we can define organization, people. So if I have Elon Musk, for example, Elon Musk will be identified as beginning of a person and the inside of a person, right? Because I have person, yeah, because I have Elon Musk that is referring to a given person. So we can define different classes, and we actually can define a specific class that is not an entity, the in any class that is a majority class, because for the majority of the words we have no a reference to a specific entity. So we have a majority class, and then we have, for each class we actually have two different classes. One is the B, so the beginning of the entity, and then the internal of the entity. And the EX class, so the internal version of the class, always follows the beginning of the class. So this high person, so the inside of the person entity, follows the beginning of the person entity. So we have those kind of rules. The idea is that we can use the same architecture we had before. So we have the BERT architecture. We have the sequence of tokens that are passed to the BERT architecture. We have all the representations that are the output of the model, and we can then have a dense layer as output of each token. So we can have, similarly to what we had for the classification part. For the classification part, what we had is a dense layer on top of the classification token. Instead here we have a dense layer on top of each token. The idea is that we don't have a dense layer for each token, but we have a shared, we have actually a single dense layer that we can share between all the tokens. So the idea is that those representation will be the input examples for this dense layer that has the parameters of the dense layer that are shared across all the tokens. And then we can have different training examples here, and we can have the correct label, and we can backpropagate, and we can do always the same procedure, but in this case we are classifying each token in the sequence. Is it clear, this part, for all of you? Okay. So the idea is that in this case, we need to do some specific trick to prepare our data, because we are dealing with token level classification, and we need to align actually the token and the classes if we don't have those aligned information. So here the idea is that we have this information. So for 2 weeks dot Empire State Building, so we have no class, not an entity class, not an entity class, not an entity class, and so on. And then Empire State Building is a beginning of a location, is an inside of a location, and inside of a location. So we have the aligned version of the token and the associated class. So here, begin of the location, inside of the location, and so on and so forth. We can tag each token to its corresponding number, so its corresponding token ID. And so we can use our tokenizer to encode our training and validation data. And actually here we can define some functions that are able to encode our tags and our labels. So we have because we have the sentence with with some words. So word 1, word 2, word 3, word 4, and we have label 1, label 2, label 3, and label 4. So we have an aligned version of those two informations. So I reported I unroll this information together, so the labels together with the encodings. Encodings are the output of the tokenizer. And so because they were not, it can happen that a word is split into two different subtokens. It can happen that word 2 is actually split into word 2 and word 2 1. I don't know, like another part of the word. So yeah, word 2 can be split into word 2 1 and word 2 2. So I can use this offset mapping, is a information given by the tokenizer that is able to that allows me to reconstruct the information about the fact that two tokens refers to the same words. So if I unroll this information together, I can associate each label to a given token, and with some tricks here, I have the encoded labels. So I have the labels that, if, for example, if this one is an inside of a person, I can split L2 in two inside of a person, right? Because if this word was associated with L1, I need to propagate this label, label 2, sorry. I can propagate this label to those two subwords, so L22 and L21. Is it clear why I need to do this? Because I don't have a mapping between each word to a given token, but I have the mapping is one to many. So I can have a given word mapped to multiple tokens. Okay, so I proceed in this way. I create the same way as before. So here, this stuff is necessary to create the aligned version of the labels and the tokens. So I have all the information after this part, and so I can create the same, similarly to the previous case, I can create the named entity recognition dataset, and I can then use my get item, and so I can create the dataset class that I need to train my model. So I can create my train dataset and validation dataset to then train my my model for the named entity recognition task. The additional part about the creation of the trainer and the creation of the training actually of the model is actually the same way. So using the trainer in this case, you can abstract the under the hood operation that you need to do. So iterating over the data set, backpropagating, dividing into batches, and so on and so forth. So here the code is the same as before that we had with the sequence classification part. Okay, so here just a few references for the Hugging Face library. So with this library, the Transformers library, you other than having these training interfaces, you also have some inference interfaces, such as the pipelines that you can use to run inference on the model that have been already trained for a specific task. The library supports different tasks such as text classification, question answering, masked language modeling, and so on and so forth. So the idea is that you instantiate a pipeline for a given task. You get the results by giving a given sentence as input to the pipeline, and so you get the score here. For example, here the label is negative with scored 0.999, and the score and the sentence was "I hate you," so it's correct. So if I have instead "I love you," it's a positive sentence with almost 100% of probability. So the idea is that I can use these pipeline objects to use the models that have been already pre-trained. So it's very handy if you don't need to train a new model. You have a model that is already there and you want to test and to use it. Yes, you have the this is a real output from GPT-2. The idea is that you can use this with other tasks such as text generation. So the idea is that here you have the pipeline. You give this is the university course of deep natural language processing at Politecnico di Torino. And then you give some information. The max length you want to produce is 50. So this is a the university course of deep natural language processing, and at Politecnico di Torino, it is designed for students who have the keen interest in deep linguistic processing. Actually, it can be true. And then it was starting with lecture 1, syntax processing for language processing, and so on and so forth. So this is more related to the fact that GPT is very powerful as a model. So, but yes, you can use in a few lines of code, you can use a very powerful model to generate text. And you have different pipelines also for named entity recognition. So here you have Hugging Face is a company based in New York City, and so on and so forth. And so if you run this on the model, you can identify each entity. So you have organization here, it is Hugging Face, yeah. We have organization here. You can see that here for this specific case, they not use beginning and internal. They just use one class for the entities. So you have just org. So the organization Hugging Face Inc. So this 4. Yes, those 4 related to Hugging Face. They're actually always I as class. So we have a single class for organization. But yeah, the second thing you want to notice is the fact that hugging, so this single word hugging has been divided into different words, and these two dashes, no, not dashes, but just those 2 symbols, they are used to mark the fact that this is a suffix of a given initial of the word. So this follows, this is not a word, but this is concatenated to a previous one without space. So this is a continuation of a previous word. And this is done in multiple cases. So this is how tokenizer stored information that this is a suffix and this is not a whole word itself. Okay, we have different set of classes. Yeah, so the idea is that you can use also specific models. If you use specific models, you should use also specific tokenizers, and then you can instantiate your pipeline by giving the model and the tokenizer you want to use, not just the, if you do this like with the default parameters, you will instantiate the default model. So it's like giving us as parameter the default ones. So here you can specify the parameters you want. So now I want to introduce you quickly a transformer architecture that is specifically tailored for the named entity recognition task, that is LUC. We have seen BERT in all the sources today, so we have seen BERT in different with different schemes and so on and so forth. So this is very similar to BERT. If you take only this part, you have the input token, the positional embeddings, you have some masking and so on. The idea is that LUC introduces one additional type of vectors called entity type embedding that store the information to the stored information about the type of the token. So the tokens can be words, but can also be entities that are also words, but are also entities. So you have words and entities. Entities are composed by words, and some of the words are entities. So for example, here, Beyonce is a word, but is also an entity because it's referring to the artist, Beyonce. So the idea is that it stores this additional information about the entities to specifically model the fact that we can have entities in our model. And so the idea is that you can compute the entity-aware attention. It means that when you compute the attention for the entities, you are taking the vectors, the query vectors, from a specific matrix that is referring to entities instead of words. So you have query vectors that are you have. Do you imagine the query vector stored in a matrix, and you can have the query vectors, the matrix that is decomposed in multiple parts, so word to entities. When you pay attention from a word to an entity, so you are computing the attention from a word to an entity. So the idea is that you have this query word to entity, so the vector that is used to query, given this the attention, you're computing the attention for a given word, you are using as query vector this vector coming from this query vector to entities matrix. Then you have also the entity to word matrix, that is the opposite actually, that is used to when you compute this operation. So when you compute the attention between this word with the query from this word to this one, and then you have entity to entity query when you are computing the operation between entities if you have multiple entities. So if you have multiple entities, you are computing the attention between those two. You are actually using, I use another color. So yeah, oh, okay. So you're computing the attention using this information. Okay, so you decompose the query vectors and you compute different vectors for the query for different types of tokens that can be both words, so normal words, but also specific entries. And so you have these 4 matrices. So the normal query matrix, so you have the word to entity matrix, the entity to word matrix, and the entity to entity matrix. And then the idea is that you have specific pre-training task. It's a specific pre-training task, but it's very similar to BERT, to masking language modeling. Instead of masking only normal words, you are also masking specific entities. So you randomly mask a certain percentage of entities by replacing them with a specific token, that is this mask token. The backbone architecture, so the original architecture for Nuke is Roberta, so it's the same of BERT but with the dynamic masking, and you can then fine-tune the BERT model to perform different tasks such as closed-style question answering, extractive question answering, and named entity recognition. So you can use the same approach of BERT, pre-train using a specific pre-training strategy, and then fine-tune for a lot of tasks, such as question answering, named entity recognition, entity typing, and so on. So you have different tasks that you can perform. Okay, once you have your named entity recognition model, how you can evaluate this model. The idea is that you are actually classifying the entities at token level. So you need to have a model, you have a type of metric that is able to evaluate the entity boundaries. So when it starts and ends a specific entity, sorry. So you can define different not metrics, but different numbers. In this case, you can identify which are the tokens that matches, so the correct. So in the system output, the golden annotation, you have the exact same set of labels, so they are associated to the same position and the same labels. You can have the number of times that the output of the system and the golden annotation do not match one each other. You can have partial annotation when the annotation and the system output are somewhat similar but not the same. You have missing annotation when the golden annotation is not captured by the system. And then you can use spurious annotation if you produces a response that does not exist in the golden annotation. So if you produce a class that is not part of the golden annotation. So by using this information, you define the possible, so the correct plus the incorrect plus the partial and missing. And then you define the actual. So these are from the golden most of the time. So they are taking into account the sequence from the golden, the actual, so the correct, the incorrect, the partial, and the spurious. So you define those values, and you can then define precision and recall by, for example, dividing the correct by the actual. So you have the precision, and dividing the correct by the possible, you define the recall. And in this case, yes, you can then use specific parameters to detect the partial overlap or the type of overlap, some overlap with the system entities. So you can define a specific version of precision and recall. This is to say that you have a tool that you can use when you need to define which are the correct entities and the predictions given by the model, and then you can evaluate the model by just using this evaluation. So the idea is that those metrics are able to take into account partial overlap of the entities or complete overlap or no overlap within them, and compute those kind of metrics in different modes. So in strict mode, exact mode, partial, and the type. So just matching the type and not the overlap of the sentence. You have a tool to do this, and you can use it if you need to evaluate NER systems. Another metric to evaluate NER model is called sequeval, because actually what you need to evaluate is the sequence. And the idea is that you have this tool and you can frame this task as a sequence labeling task. So for each class you can define, for each token you can define if the associated label given by the model is the same as the one that has been predicted by the model predictions is the same or of the true label in the ground truth. So here, for example, I have the true labels and the predicted labels. If I have the true label that is organization and instead I predict that I have not an entity, this is a false negative. If I have here there is a person and instead I can define false positive and false negative actually by just matching the tokens with the ground truth. And if you define false negative and false positive, false negative, true positive, and true negative, you can define a sequence of metrics that are similar to the classification task. So you can use this seqeval metric by using this code, and here you need to have the mapping between the predictions and the references given by the model, and then you can put this in this. You can compute these metrics by just computing the matching between this and this, and so you have the results, and you have for each type of entity. So this is like miscellaneous. You have persons, and then you can have the overall of the whole sequence. So you can compute the overall accuracy. Accuracy, precision, recall, and depth measure. Or for each class, you can compute the precision, recall, and depth measure. Okay, I think that's all for the evaluation. Do you have questions? No questions? Okay, I think if you want, we can conclude with a few exercises. The exercises are very similar to the ones that you can find as a final question in the written exam. These actually are aimed at evaluating your reasoning skills when you have at your disposal different tools to perform different tasks, such as name identity recognition, sequence classification, and so on. You have a real case, a real use case, and you want to describe a pipeline or a system that is able to answer this need. So you imagine your company is called Deeply. It produces IoT smart devices and wants to automatically analyze a stream of Twitter messages. Your input is a sequence of strings, the tweets, and you need to define an NLP pipeline. Yes, was in white. An NLP pipeline that is able to extract relevant knowledge from data, and you have no annotated data. How you can do this? For example, you want to analyze if people are talking about Deeply products, bad or good. A solution can be that you analyze the tweets to filter only the ones that refers to Deeply. To do this, you can load a pre-trained NER model. You use it on sentences to identify the organization if you match Deeply as an entity. You use filtered sentences, and you use a sentiment classifier. You load the pre-trained sentiment classification model. You apply it on the filtered sentences, and you can divide positive and negative sentences, and you can compute which are the products that are associated to positive reviews or negative reviews. So the idea is that you should be able to understand that you have a name identity recognition model that can be used to filter out those tweets that are not referring to Deeply products. And another thing to say here is that here I used a NER model, but I can use an information retrieval model that is able to match the words. So there is not unique answer. The idea is that you need to be able to use the tools that you have encountered during the course. Okay. Here we have the same idea, but you have an annotation budget. So imagine you are in a company and you have 5,000 euros to annotate 5,000 data samples. So how you can spend your budget, and you should justify the answer. So the idea is that if you can annotate, you can use annotations. You can use annotations in different ways. In this solution, you use no annotation on name identity recognition, but you use annotations on the, no, you don't use annotation in, you have positive and negative sentences. Yes, the idea is that you can fine tune the name identity recognition system to recognize Deeply products. So if you have your products that are named in a specific manner. So you have, I don't know, model 1 and model 2. You can use those annotations to fine-tune the entity recognition model that is able to recognize the name of given products. So in this case, we choose to use the annotations in the named entity recognition part. So yeah, there is no unique answer. The reasons behind the annotations should be suitable for the use case. We have no annotation in this case, no annotation in this case. Yes, the idea is that we are not using the fine-tuning for the named entity recognition for a specific tweet on Deeply, but for a specific tweet on the product or on Deeply, just because perhaps the name of the products are very difficult to recognize for a general purpose named entity recognition systems. Yeah. So yeah, we have additional questions, but I think we are almost at the end. If you take a look at those questions, and if you have questions on this, please ask me. Then the last part is just a list of tools that you can use to go from development to production. So if you have a deep learning model that is able to solve real world tasks such as text classification, similarity search, text generation, and so on, you have actually very high computational requirements. So the deployment of the model in a real product in the real world can be an engineering problem. So the idea is that when you deploy this model, it should be fast and reliable, and it should be easy to use from a developer perspective. So the idea is that first you need to have some sort of dedicated hardware, because if you compare the performance of those models on CPU and GPUs, this is a very low-end GPU, and even on low-end GPU, you have one order of magnitude of difference between the timing of the CPU and the TPU. So be aware to the fact that GPU and TPUs greatly speed up the whole process of inference on those models. How you can deploy this really? You can use Docker. That is a way to create an environment, a specific environment to satisfy all your dependencies in terms of libraries, in terms of things. When you have your product working in a given environment, you can clone it on Docker, and then you can deploy it on multiple machines. You can use some libraries such as the transformer library, that it can be used to build deep learning based pipelines. So you can use transformers to build this pipeline. You can then use FastAPI as a framework to develop the API to access your model. And finally, you can use some sort of cloud platforms such as Google. You have several alternatives for this to deploy your application to the real world. So these are just pointers that you can use to refer if you want to actually deploy your models. So that's all for the lessons. If you don't have access to the Discord, please ask me, send me an email. I will give you the link to access Discord. Do you have final questions? Even online, do you have questions? Okay, if you don't have any additional question, we can close the lesson now. And so have a nice weekend, and see you next week on the lab. Bye.